On the 1st of July, 2025, astronomers using the Atlas survey in Chile spotted something unusual. At first glance, it looked like a distant comet, just a faint blur against the starry background. But almost immediately, the data didn't add up. Its speed was off the charts, about 221,000 kilometers per hour, or 137,000 miles per hour. That's faster than 99% of the comets we've ever tracked inside our solar system. Its path was even stranger. Instead of looping around the sun like a native comet would, the orbit calculations showed something extraordinary. This object wasn't bound to our solar system at all. Its trajectory was hyperbolic, meaning it came from the vast interstellar void and would leave just as quickly. Astronomers realized they were looking at only the third confirmed interstellar visitor in human history. Officially, it was named 3I Atlas, marking its place as the third known interstellar object. But right from the start, Atlas looked different from anything we'd seen before. It wasn't behaving like a normal comet. Some thought it might be a natural fragment of rock and ice, but its unusual brightness, odd energy signatures, and controlled-looking trajectory whispered of something stranger. Behind closed doors, a chilling possibility surfaced. What if this wasn't just a comet, but technology? A nuclear-powered craft drifting into our solar system, built by someone or something not from Earth. To grasp why Atlas sparked so much excitement and suspicion, you have to look back at its predecessors. Before 2017, interstellar visitors were only a theory. Scientists assumed that from time to time, objects must be kicked out of their home star systems and wander into new ones. But it had never been proven until Oumuamua arrived. Discovered in October 2017, Oumuamua was long and cigar-shaped, at least 100 meters across. And it did something no one expected. It accelerated slightly as it left the sun, without a cometary tail to explain it. Some researchers said this could be caused by outgassing too faint for telescopes to see. Others, like Harvard astronomer Avi Loeb, openly suggested it might be alien technology. The debate never ended. Then in 2019, Comet Borisov entered the stage. Unlike Oumuamua, Borisov looked and behaved like a typical comet, shedding gas and dust as it neared the sun. It reassured scientists that not every interstellar visitor was so bizarre, but it also proved something profound. Our solar system was not isolated. There is real traffic between stars. By the time Atlas arrived in 2025, humanity already had a history with interstellar objects. Yet Atlas seemed to combine the strangest qualities of both its predecessors. Like Oumuamua, it moved in ways that looked too precise to be random. Like Borisov, it showed comet-like features but twisted in ways no comet should. That's why astronomers quickly realized this wasn't just another rock passing through. Atlas could be the one that changes everything. To answer the puzzle of what was driving Atlas's early outbursts, astronomers turned to the most powerful tool available, the James Webb Space Telescope. With its ability to peer into the infrared spectrum, JWST could reveal the molecular composition of the comet's coma, the cloud of gas and dust surrounding its nucleus. In late August 2025, Webb pointed its near-infrared spectrograph toward Atlas. The results were nothing short of astonishing. The spectrum showed that the comet's coma was dominated by carbon dioxide. In fact, the ratio of CO2 to water vapor was measured at about 8:1, making Atlas one of the most carbon dioxide-rich comets ever studied. This alone set it apart from the majority of comets within our solar system, where water typically dominates. But CO2 wasn't the only ingredient Webb uncovered. Alongside it, JWST detected signatures of water vapor and carbon monoxide, as well as more exotic compounds like OCS, a sulfur-bearing molecule. Ice grains and dust particles were also present, evidence of ongoing sublimation and erosion as the comet interacted with sunlight. Even more intriguing, Webb's observations revealed that the outgassing wasn't uniform. The emissions were stronger on the sunward side of the comet, suggesting that direct solar heating was driving these chemical releases. This confirmed that sunlight was actively powering its strange and early activity, but the overwhelming dominance of CO2 indicated that Atlas had formed under very different conditions from most comets we know. The mystery deepened further when astronomers compared JWST's results with data from other observatories. As striking as the CO2 was, another space telescope soon revealed a different and equally puzzling chemical signal, one that shouldn't have been possible at the comet's distance from the Sun. While Webb's infrared eye exposed Atlas's unusual chemistry, another observatory caught something that defied expectations even more. The Neil Gehrels Swift Observatory detected emissions of OH, a fragment molecule that forms when sunlight breaks apart water. In comet science, OH is a telltale fingerprint of water vapor, and what Swift found between July 31st and August 1st, 2025, shocked astronomers. At the time of the detection, Atlas was still about 3.5 astronomical units from the Sun, farther than the orbit of Mars, and well beyond the region where most comets are too cold for water ice to sublimate. Yet here it was, releasing water into space at a staggering rate. The numbers were remarkable, about 40 kilograms of water per second. This wasn't just a trickle of vapor. It meant that an unusually large portion of the comet's surface was active, far greater than what scientists typically see at such distances. For comparison, most comets don't begin releasing water at significant rates until they're much closer to the Sun. Atlas was breaking yet another rule. The implication was clear. Atlas must have formed in a region of its home system that was extremely cold, near its carbon dioxide ice line, where CO2 and water ices could exist together. Its strange CO2 dominance and this early release of water vapor pointed toward an origin radically different from the comets that formed in our solar system. With two space telescopes now confirming its bizarre activity, astronomers began to realize Atlas wasn't just chemically unusual. It was actively rewriting what we thought we knew about interstellar visitors. But the surprises weren't over. As the comet moved closer to the Sun, ground-based observatories revealed that it wasn't only its chemistry that was changing, but also its appearance. By September 2025, Atlas had already become one of the most closely watched objects in the sky. Observations from the Gemini South Telescope in Chile confirmed what many astronomers had anticipated. Its tail was rapidly expanding. The comet's coma, that glowing envelope of dust and gas, was swelling as it absorbed more sunlight, scattering light across space and making the comet steadily brighter. But brightness was only part of the story. Photometric data gathered from the Atlas Survey Network, covering the months of March through August 2025, revealed that Atlas was changing in another, unexpected way. Its color. Initially, the comet displayed a deep red hue, typical of objects rich in organic compounds and darker ices. Yet as its anti-solar tail grew more prominent, that redness faded, replaced by a tone closer to the color of sunlight itself. This wasn't just a cosmetic change. It coincided with a sharp shift in the comet's brightness pattern, known as a slope break, which occurred when Atlas reached about 3.3 astronomical units from the Sun. The timing suggested that as more of its volatile ices began to sublimate, its dust production ramped up, scattering sunlight differently and altering the way the comet appeared to observers on Earth. In essence, Atlas was transforming before our eyes, not just growing brighter, but evolving in color and composition as it journeyed deeper into the solar system. And yet, these dramatic visual changes were only a prelude to another mystery that cut to the very heart of what makes comets unique: their dust. Just when scientists thought Atlas couldn't surprise them any further, its dust revealed something almost unheard of. In early September 2025, astronomers began carefully measuring the way light scattered off particles in its coma, using a technique called polarimetry. This method looks at how sunlight becomes polarized or oriented after bouncing off dust grains, and it can reveal a great deal about their size, shape, and composition. What they found was nothing short of astonishing. Atlas showed an extreme negative polarization branch, plunging to -2.7% at phase angles of about 7 degrees. For context, most comets in our solar system exhibit only mild, negative polarization, and even then, rarely this deep. Atlas, however, was breaking that rule entirely, producing a signal that suggested its dust was unlike anything we typically encounter. Why does this matter? Because such unusual scattering behavior points to dust grains with strange properties, perhaps highly porous, irregular in shape, or made of exotic material that doesn't exist in the comets born in our own solar system. In other words, Atlas may be carrying dust that formed under alien conditions in an environment shaped by a completely different star. This rare signature immediately set Atlas apart as a kind of dust outlier, forcing scientists to rethink what cometary material can look like. And yet, while its dust hinted at something truly foreign, one of the biggest mysteries remained unsolved. Just how large was Atlas itself? For all the data pouring in about Atlas's chemistry and dust, one of the most basic questions remained surprisingly elusive. How big was this interstellar comet really? At first, astronomers tried estimating its size based on brightness. Those early calculations suggested its nucleus, the solid core hidden beneath all the gas and dust, might be only a few kilometers across. But there was a problem. The sheer amount of material streaming from Atlas made those estimates uncertain, because its dazzling coma masked the actual body beneath. Then came another twist. Pre-discovery observations from the Vera C. Rubin Observatory hinted that Atlas could be significantly larger than initial guesses. The discrepancy meant scientists were working with two competing pictures, one of a relatively modest comet and another of a much bulkier traveler carrying a greater reservoir of ices. Until the outgassing calms enough for the nucleus to be glimpsed more directly, its true size will remain hidden in mystery. But its composition already told a powerful story. With a chemistry dominated by carbon dioxide, Atlas likely originated in the coldest reaches of its home star system, far beyond the region where water ice can condense. This would make its birthplace similar to the Kuiper Belt, or the distant Oort cloud in our own solar system, places where frigid temperatures preserve fragile ices for billions of years. What makes Atlas even more fascinating is how different it is from the two interstellar objects before it. Oumuamua was dry and oddly accelerating. Borisov looked more like a typical comet, though it hailed from another star. And now Atlas, with its volatile CO2, unusual dust, and possible large nucleus, added a third, entirely different profile to the list. 3 interstellar visitors, 3 very different stories. Together, they suggest one striking truth. Planetary systems across the galaxy may be far more diverse than we've ever imagined. And this brings us to the final, most important question. What does Atlas actually mean for us here on Earth? Atlas was never just a comet. From the moment it streaked into our skies, it carried with it a bigger meaning, one that stretched far beyond a single object of ice and dust. Atlas was a messenger, a fragment of another star system that had wandered across the light years to knock on our door. Its strange chemistry, its alien dust, its early and unusual outgassing, every signal it gave, was a clue about worlds we may never see, but which exist out there all the same. Its carbon dioxide dominance proved that not all systems forge comets the way ours does. Its rare negative polarization revealed dust structures that don't exist here. Its early bursts of water shattered what we thought we knew about when comets awaken. Atlas wasn't just rewriting our textbooks, it was whispering secrets of alien birthplaces light years away. And then comes the bigger picture. Humanity had never seen a single interstellar traveler. But in less than a decade, 3 have arrived. Oumuamua in 2017, Borisov in 2019, and now Atlas in 2025. 3 visitors, back to back, after an eternity of silence. Is that mere chance? Or a signal that the galaxy is far busier than we ever imagined? But the most unsettling question of all is this. What if these objects aren't random wanderers at all? What if they are connected a chain of probes, natural or artificial, drifting silently between the stars? If that's true, then Atlas wasn't just a comet. It was a piece of something far larger and far stranger. Because whether it was born of alien cold or crafted by alien hands, Atlas leaves us with one haunting certainty. It will not be the last. Somewhere out there, another interstellar messenger is already on its way, and next time, it may not just pass us by.